All right, I've got bad news and I got worse news. The bad news is that the weather's crap, and the worst news is you're here to listen to me. All right, show and tell. These will be moving around the room. This is a P100 mechanical sample. It's one of the ASICs I've worked on. You can pass that around if you would. This is Q200. It's the one that came out before that. I guess I can move these around. Super fancy. This I managed to liberate from some friends of mine at TE Connectivity at the OCP Summit. This is what we call a flyover cable assembly, which is basically one of the ways that we're solving the problem that physics starts to get in the way on the printed circuit boards that we've been building for 25 years. So when I talk about it, you're like, oh, that's what that little doodad is. So if you want to swing those, I do need those back. Actually, to be honest, they're not incredibly valuable, but then the next time I do this, they won't have any, I won't have my show and tell parts. All right. Mandatory administrative stuff. Turns out we have an app. You should use the app. They fire me if I don't say use the app, so use the app. They also make me put an agenda together. Who here has been to one of my talks before? Anybody? A couple of you have. All right. If you haven't, I don't tend to pay a lot of attention to my own agenda. But it's one of those things that they're like, it has to have an agenda. Oh, okay. Another one of my big rules is we don't read our own agenda. So if you can't read, sorry, I'm not picking on you, but this is more or less what we're going to talk about. This is me. I started at Cisco in May of 1997. If you want to see my directory photo, I'm not old enough to legally buy beer in the United States, although I guess I would have been here. I was in the RTP TAC for a couple years as a uni intern. I was on this thing called the ISP expert team for a couple of years, which was, at the time, folks like AOL and UUNet and SprintLink. Back then, before Google, we called that the internet. And basically, when somebody broke a 7500 or a GSR, the team I was on got the call and we had to fix it. I was a TME for basically everything in the big routing universe, GSR, CRS, when we started doing iOS XR, all those platforms. I spent some time in advanced services. It's probably no longer deployed, but if you ever flew through the Denver airport and the Wi-Fi didn't work, it was probably my fault, because I designed that network when they rebuilt that terminal. I took a year sabbatical off from Cisco at a company called Barefoot Networks, which built programmable forwarding silicon. They ended up getting acquired by Intel a little bit later. The Tofino chip was what we worked on, and they ran that for a couple of generations. And sadly, it is no longer with us. Although the programming language, which is called P4, is the thing that we use in the Silicon One chips. So if you want to go downstairs to the real show and tell area, back in the corner, back on the back wall, there's a setup with all the displays of the chips we build. And that's what I've been doing since I came back to Cisco in 2015. The lawyers say that I have to tell you that this comes as a great shock. There's some AI-generated photos in here, but I am not yet AI-generated, although I think that check is probably in the mail. So what are we going to talk about? Well, we're going to try to talk about mostly hardware. I'm going to try really, really hard to not say the word software very much. Not that I don't like our software friends, but I think it's kind of disproportionately represented in the things that we talk about here. And the folks that set the schedule allow me to come up here and talk about things that most people don't talk about. Where I sort of got to was I put this whole thing together, and I started doing these maybe 4 or 5 years ago. 15 years ago, when we're doing GSR and CRS, there was real mechanical engineering in how to build these things, for sure. But it was mostly downstream of building the other stuff, right? It was like, this is the chip, it's this big, put it on the board, how much power do we need? Well, we don't know for sure, but we know that we'll have it, right? And so somebody would basically do the board design, figure out a way to make it all fit, and then just say, okay, the power budget is X, and we would go to one of the half dozen or so people who build power supplies and say, we need one that's this big. And they would say, okay, here. That is no longer how this works. The amount of power that we use, the concentration of the power, so one of the secret decoder rings for almost the entire presentation is, if you hear somebody who talks about system design say the word power, they probably mean heat. Like it is much, 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 much easier to get the watts into the system than it is to distribute them throughout the system and to get the heat back out. generally speaking. Not to say that the power supply designs are trivial, because they're not. But a lot of what we come down to is really thermal challenges. When we say mechanical, a lot of times that's kind of a code word for thermal. The presentation is slightly circular, so at some point you're going to be about minute 70, and you're going to go, didn't he already talk about that? And that's sort of by design. And it is definitely tries to be more broad than it does deep. I do want folks, turns out they wouldn't let me do a 3-hour interactive breakout where we all sit in a room and everybody gets to ask their questions. But I do want folks to come up with questions, like when you see something and go, I don't understand, why did they build that thing? Why is this sideways instead of right side up or whatever? Like, think about that, and then when we're almost done, I want folks to ask that, because I think at some point the real value in this is getting a chance to ask the questions that, to me, even this stuff isn't even obvious now, but having done it for 10 years, I remember 10 years ago, some of the stuff was it was completely unclear to me why we did some of this stuff. And almost the only way you figure it out is you ask. And so one of the things I want to do is give people a chance to ask. All right. Really, really big themes, right? Kind of the whole theme of the presentation, right? Hardware's really hard. The greatest part about working in a software job, or writing software features, or managing software features, is you can just recompile it, right? I always joke that there are problems in my world when somebody says, oh, I need feature X, Y, Z, blah, 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 blah. I can, point a metaphorical gun at somebody and say, go into that room and don't come out until it compiles. That's a software problem. In the hardware world, we can't do that, right? If I screw up one of those chips that's running around the room so bad that I have to respin it, that is something like 6 months and millions of dollars. Like, imagine how careful your software engineers would be if it cost them $1 million and took 6 months to fix a bug, right? So there's just a completely different mindset. It takes a long time to change things, and one of the things you will hear me say in every presentation I do is that all of what we do is just about trade-offs and optimizations, right? The least favorite thing, and I guarantee you that you will see it here somewhere if you go to enough presentations, somebody will stand up on one of these fancy stages and say something like, here at the Cisco 17469B.7, we have absolutely no compromises. It's amazing. Quite politely, that person is full of it. There is no such thing as an engineering system with no compromises, right? That's not a thing. That's not how it works. What it does come down to is all of these designs are basically a tug of war between two competing things, right? Some of them are in tension, and some of them are in outright opposition, right? I can take one of those chips running around, and I can certainly make it faster, right? I can make different design choices that increase the number of packets per second or the number of bits per second that go through that thing. What I cannot do is that without giving up something else, right? So one of my running jokes is, when they bury me and they write on my Cisco tombstone, one of the things that it's going to say is, don't ever ask a customer what they want, because they'll tell you, right? Ask a customer what they want more. Because ultimately, if I say, do you want all 27 things? The answer is like, of course, we want everything. That's not a usable piece of information, right? The usable piece of information is, what would you rather have, right? I can make it faster, but it's going to use more power. Or I can make it use less power, but it's going to be bigger, right? And so all of these trade-offs, when you look at something and go, why is this shaped the way it is? The answer is usually because somebody had to make a trade-off. Another super important thing is, at some point, most of these trade-offs become nonlinear, right? The exchange rate changes. And so when somebody says, this thing that was built 10 years ago, grew to this big, and it didn't look like it was all that hard, but now it's completely different, usually the answer is somewhere in the physics universe. And I promise I don't actually know any physics. I don't actually know any engineering either. But one of the things I have realized is that when things start to get much more difficult as opposed to just more difficult, that's when you have to start making different decisions, right? And a lot of what we're going to talk about with like the signal integrity parts is basically when we went from running things at 0.5 gigahertz to running them at 1 gigahertz to running them at 5 gigahertz. Like, it's not that that wasn't hard, but it wasn't really hard. But as we start getting towards tens of gigahertz and hundreds of gigahertz, and we're trying to drive these signals over You know, if you think about one of these big chassis and kind of draw in your mind how far the signal's got to go from whatever the far end of the system is to the opposite end of the system, like that's far. It can end up being a couple of meters worth of copper traces. Driving those signals that far at that speed gets extraordinarily expensive. And you have to start making all kinds of really unpleasant trade-offs, right? You either have to throw more silicon at it or you have to throw more power at it. There's just lots and lots and lots of like nasty choices that you have to make. And so the way I frame that is basically the exchange rate for making something better in one dimension doesn't stay the same over time, right? What it cost me to, I'll make it up, what it cost me to increase the bandwidth by 50% 20 years ago is not the same thing that it cost me to make that same step change today, right? It might be in different units, right? Maybe in the old days it was space and now it's power, and maybe the old exchange rate was 25% and the new exchange rate is 100%. And the point is not to have people know what those rates are. That's for the real engineers to handle. The point is for us to understand that these things, when they start to bend like this, you probably need a really good reason to be way over here, which is not to say that they don't exist. There are plenty of good reasons to live out on the edge, but it gets really expensive to live out on the edge, right? When you really start to constrain things, like, you know, in the hyperscale world where I spend a lot of my time, they care a lot about bandwidth and power. And they're willing to forego almost anything else to get to that, right? You know, they're willing to spend astronomical amounts of money so I can go and fab the absolute most current generation chip, you know, at TSMC in Taiwan at 3 nanometers, blah, 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 because they need that to run the business. The vast majority of people do not care, right? They need something that pings, preferably most of the time. And so it's a different set of trade-offs. All right, real quickly, how do we get the power in, or how do we generate the power, and how do we get the power in? We do a presentation that you probably find on the web somewhere where we talk a little more about like the big infrastructure. This guy down here, this is a 600 megawatt gas turbine. Everybody knows the reference 1.21 gigawatts, I assume. That's 1,200 megawatts, which is about a fifth of the entire state of Victoria's average power consumption. So these data centers that folks are talking about building, or in some cases already building, are more power than basically the population of Australia uses to, and in some cases the population of the United States uses to heat and cool and power their homes. These are astronomical numbers. And the power has to come from somewhere, right? And so a lot of it ends up being, you know, the stuff that ends up being added is often gas turbines because they're, relatively speaking, easy, quick, and cheap to get in the ground, right? You can basically pour a giant slab of concrete, call your friends at General Electric, and say, hey, can you deliver me a 500 megawatt gas turbine that weighs 400 tons in less than 20 years? And they're like, oh yeah, we can do it in less than 20 years. Whereas if you talk about building like an entire, you know, don't even get me started on how long it takes to build a nuclear plant, but even these really big thermal plants, you know, they take decades to plan. So once we generate the power, we've got to get it from wherever it's built into the router so we can switch packets with it. Over here on the right, this is from that other presentation. I'm not going to spend too much time on it. You basically have these, you know, extremely high voltage sources, hundreds of kilovolts, and then there's this whole energy distribution network, which is another 3-hour presentation in and of itself that at some point I'd like to do because it's fascinating. And you build all this infrastructure and you wire all this stuff together, and eventually you hand anywhere from a few hundred to a couple 10,000 volts off to the facility somewhere, right? And then there are rooms full of equipment, most of which have never been allowed into because the stuff in there will absolutely kill you if you do it wrong. And then, you know, they drag copper or aluminum wires, something like that big, over the ceiling and into the room where the stuff that we play around with lives. And inside the system, the power distribution looks something like this. And so in the building, the transfer switches, the distribution panels, a huge amount of energy goes into keeping these systems cool. We'll talk about that in a little bit. And then once you get to here, the power distribution unit, down here you're down to a couple hundred volts. You're usually down to a couple hundred volts, and for an individual system, if you're in the DC domain, you're usually in the 40 to 70 range. We're starting to see some uptick in high voltage DC, but you're in that order of magnitude. by the time it gets to the NPU, right, the chip that's running around the thing, that one, the bigger one, runs at, I think, 1.3 volts. Some of these chips burn 1,000 watts. You don't have to have much of an engineering degree that if you do the math, if you're doing 1,000 watts at just over a volt, that's almost 1,000 amps of current. That's a lot of current, especially for something that's only this big. And so you've got this entire board design, universe where you've got to figure out how do I get that much power in? And we're not talking about, it can't just be any power. It has to be incredibly clean power because those transistors do not like to be wiggled the wrong way. The voltage has to be exceptionally flat. And then, of course, as you see in the schematic here, every time you do one of these transformations, you have some amount of loss. And when we say loss, what we really mean is heat. And when we say heat, what we really mean is now I have to run the air conditioner to get the heat back out of the building, otherwise it melts. And it turns out that routers don't like to be melted. All of which is to say, a little bit of free career advice. I joke that it's worth what you're paying for it. Do you know your facilities people yet? Because if you're planning on working in this space for very much longer, you're probably going to need to. One of the analogies I sort of came up with was what we sort of saw maybe starting 30, going to about 10 years ago, where you used to have really, really significant separations between the optical or transport folks and the network or routing folks, and everybody has slightly different words for it. But they were pretty separate organizationally, and half the time they didn't even really like each other, and half the time they didn't talk. I think we're there with the power now, because you can't run these networks and you can't run these infrastructures without really starting to understand where the power comes from, how much it costs, and how much more you're going to be able to get. Because it turns out that in an awful lot of the designs we do, like some people used to ask me, how big is the router? Right? And what they were really asking was how tall? How many rack units? 10, 20, 44, whatever. For the most part, it doesn't really matter that anymore. And the reason it doesn't matter is because everybody's got more space than they do power, right? Somebody says, how big is the router? And I say, it's two 3,000 watt power supplies. And they say, oh, that's 4 racks. And I'm like, no, it's only this big. They're like, right, but it's 4 racks. I'm like, right. So don't ask me how tall it is, ask me how much power it uses. All right, so how do we build these things? Every time we step down a voltage, and it's almost always down, right, because it starts at hundreds of thousands of volts coming out of the power plant and ends up at 1 volt going into the little chip. Inside the chassis, one of the mechanical engineering challenges that we have to do a lot of math on and think about is literally a bus bar, right? And that is, in some of these big chassis, a bar of copper that's about that big that basically runs the spine of the system. And turns out copper's not cheap, so everybody's like, does this really need to be $1,000 worth of copper? And somebody goes off and sharpens the pencil and says, volts, amps, resistance, loss, math, thing. Yep, it's got to be that big. And then the person who wants it to be cheaper says, okay, can we get copper any cheaper? And so one of the things that we want to try and optimize for is having as few of those transformations as we can, right? Because every time you do one, if I can go from 54 volts to 3 to 1, that's better than going 54 to 12 to 3 to 1, right? I save that one-step transformation. Can't always do that, but it's one of the things we try to do. Once we get the power in, right, every watt that goes into the system comes out as either heat or light, right? Some guy, Einstein, said something about conservation of energy. I don't know. I don't understand it. But I'm quite confident that every watt that goes in is a watt that comes out. And it turns out that the watt that comes out in light is measured in milliwatts. Like it is not 0, and you can measure it, but it is effectively rounds to 0. So basically, every watt of energy that goes into the system comes out as heat, and I've got to get that heat out of there somewhere. Fans are super easy to understand, right? You go, and the air goes past and picks up some heat, and it's great. The problem is that there's some really, really painful mechanical engineering, they're literally called the fan affinity laws, that make this get really expensive, right? So if I want to double, this is the plot here, is the airflow is the thing that I really care about, right? If I want to take more heat off one of those chips, I need more airflow. right? That's one of the terms in the equation. So if I want more airflow, how do I do that? Well, I either get a bigger fan or I spin it faster. If I spin it faster, it follows these laws. If I want to double the airflow, I square the air pressure and I cube the amount of power that I use. This gets super painful, right? There are systems I work on where moving the ambient temperature 3 or 4 degrees centigrade can be 10,000 watts of power on the fans. And it also sounds like an A380 taking off, but that's a separate problem. This is one of those nonlinearities I talked about, right? One of the things that, and I have this conversation with customers all the time, like, if you can get the facilities people to promise that the room will never be more than 35, instead of never be more than 40, which in some places is totally reasonable and in some places is not, the amount of power that you need to provision to spin the fans in that worst case can be thousands of watts. And thousands of watts can be tens of thousands of dollars a year. Like, this is where the facilities people and the networking people have to sit in the same room at some point, because everybody's got a budget, right? But at some point, those budgets merge. And if I can go in and say, hey, look, figure out what it will cost to keep the room a little cooler, that's some number. And then you say, now I can go look at all the equipment. And this applies equally to servers and GPUs and all that sort of stuff. There's nothing super, super unique about networking gear here. But if I can save 2,000 watts of power, that's several $1,000s a year. And at some point, several $1,000s a year, especially if you've got a whole bunch of these systems, it starts to add up to enough where you can get a facilities project off the ground. We'll talk about liquid cooling later. Liquid cooling is better in every dimension except the dimensions it's not better. So some of the systems we build, right? Every one of these types of systems, if you will, has kind of its own set of challenges. This is the 8812 and this is the 8818. These are the really, really big systems that I spend a lot of time on. You've got to have a bunch of line cards. You have to have everything be field replaceable, right? I got to be like, this is literally the empty chassis, and you put about 75 other things in it before it will actually switch packets. And there's like, you have to have rails and you have to have pins and you have to have connectors and you have to test all this stuff. So there's a lot of complexity that literally just goes into how do I physically assemble the thing. There's complexity in how do I ship it. Some of these systems, especially this guy over here, we're actually at the point where if you look at the fabric card that goes in the back, it's about that tall, which is the largest printed circuit board that anyone on the planet will build. And if somebody says, oh, I'd like to make the fabric card bigger, we say, we can't, because there's no one we can get to build the thing. And so you get into all sorts of stuff. It's got a gigantic amount of total power. This is a cute little screenshot. I was asking one of our mechanical engineers I was actually asking for pictures that I could use in this presentation. And I said, hey, I'm looking for somebody, because I live in the big router world. I said, I'm looking for somebody who knows how all this like industrial and hardened switching stuff works. Like, you go downstairs, they've got all kinds of cool shit down there. And he was like, you calling this stuff small? And I was like, well, and this is a little hard to read. I said, this procedure outlines the steps for installing the pull bars on the 8818 chassis. The pull bars serve as an aid for moving the chassis to the lifting device. Don't pull the chassis by the pull bars. You only use the pull bars to get it near the forklift or whatever the hell it is that you're using to move this thing. That's how big it is. And so there's this whole other, they're like people who have whole jobs and all they have to do is figure out how to safely move and maneuver this gigantic chassis to the thing that is designed to actually move the chassis. Then you get to like the opposite end of this, like the little switches, right? Here we care a lot about port density. We care about a lot about how much volume do I actually have, right? We end up running into cases where like I can make connectors and optical couplers and things like that that are so small that your fingers don't work anymore, right? Does anybody remember the mini SMB connectors from back in the telco days? Like, you had your old DS3 T3s that were like that big around, and they were really easy to mess with your fingers. And this stuff just kept getting smaller and smaller and smaller. Do I have them on this chassis? I don't. Like the little tiny copper timing ports on the front of all these switches, like we're getting to the point where you have a genuine maintenance issue, and somebody goes in and says, I can't get to the thing because I can't get my fingers there without unplugging something else. Now, if you're in a lab and you're like, oh, we'll just unplug the management Ethernet so I can move the timing port, that's not a big deal. In a production network, turns out it's a really big deal. So there's like all of these like second and third order design constraints that are really, really complicated. The little chassis, not surprisingly, little chassis have little fans, and that's not great because the little fans, in order to move that much air, have to spin a lot faster, and in order to spin a lot faster, go back 3 slides, and the power curve does this, right? So all other things being equal, I would almost always rather have larger chassis that I can have larger fans because they're more efficient. And then you get into like some of the not purely technical challenges. There's not really a standard depth anywhere, right? Somebody will say, oh, this needs to go in a 300 millimeter cabinet. Okay. What are we measuring with 300 millimeters? Is that from the rail to the rail or the door to the door? Am I allowed to count the optics that go in the front of the switch? Am I allowed to count the bend radius for the optical fibers that come out of the optics that go into the switch? And so there's all of these challenges. These are my problems, not yours, that exist around like these, there are standards in some places, but there's not really standards everywhere. Width, that one's pretty standard, right? The standard 19-inch EIA rack, that's been around for 40 years and hasn't really changed. We all pretty much agree on what a rack unit is, although we don't seem to agree on how many of them there should be in a rack, which I've always thought was kind of funny. And so when somebody says, oh, does it fit in a rack? I don't know, which rack? And they say a standard rack, and I say, please don't say that. And then you get to depth, and it's like, oh, hell no. Like, there's just no, and I'm like, look, just like draw me a top-down schematic and say, this is what I'm trying to get it into. This is where the door is. This is where the rails are. Will the thing fit? And we say yes or no. When you start getting into this is an area that I would love to go work in at some point. Right, there's this whole fleet, and if you haven't walked the World Solutions, go down and look at this little section of it. They must have 85 different devices down there that are all like very subtly different flavors of mechanically optimized for some problem, right? They're like, oh, this is the switch that we put in the cabinet that sits at the side of the railroad track. Okay, that's cool. They're like, which is different than the one that we put in the cabinet that sits at the side of the highway. Okay, why is it different? And they have some answer, right? But it's like there's all of these different things, and you go in, and they all have these different market segments. And some of it is because they have different voltages, and some of it is because they have different other protocols that some of which have been around for centuries. But you've got all of this like really complicated mechanical engineering that has to go into this stuff, right? All these guys, they have these basically, threaded big connectors. Like this is just Ethernet, right? Ethernet's 2 or 4 wires, and they're really tiny, and we don't need all this stuff. But if you want to make it so that when you dunk the thing under 30 meters of salt water, it still works, there's a whole ecosystem that has to go and figure out, like, how do I build a connector that solves this problem? Right? And then you've got some of it is carrying data, and some of it is carrying power, and you've got a whole different set of universes when you try to run power underwater. So anyway, wander around downstairs and look at some of that stuff because it's actually really super cool. No rubber duckies were harmed during the testing of this system, and all those things, right? You have to most of this stuff. There are standards for if it meets IP67. This is not my world. That basically means that you can shake it some amount of hard, you can hit it some amount of hard, you can bury it some amount of deep underwater, all these sorts of things. So this is kind of like we've got a giant shaker table. I turned the audio off. You'll thank me later because it sounds like a jackhammer. And they literally wire this thing up and send traffic through it and then just shake the crap out of it for hours and hours and hours. There's a dust test. You basically put this thing in an environmental chamber. And it's not just any dust, because there's a standard. It has to be like the right dust. And like one of the things that we're running into in these big AI clusters now is you're getting little tiny specks of dust, like PM2.5 type size dust particles. And if they get between the end of the optical fiber and the transceiver, you get just enough error, like as the system moves a little bit and that particle of dust wiggles, you can get just enough interference that it flaps the link for an incredibly short period of time, which back in the telco days, we just kind of ignored, right? We were like, oh, yeah, 10 packets, whatever, we don't care. It's a micro of a microsecond. Well, the AI people, they don't like losing packets. So when you do that, it basically restarts the whole job and they get really, really mad. So we've spent a lot of time in the last few months trying to figure out, like, do we have to replace the filtration system for all of these giant data centers with stuff that we haven't thought about how we're going to engineer yet, because we didn't know that even really clean air isn't really all that clean. Hose down testing, this is great, right? Just like you literally just plug the thing in and spray it. This is one, I have no idea how you can build something that passes this test. You literally take salt water, steam it, evaporate it, shove the system in the cabinet, and let it all condense. Salt conducts electricity. Like, we don't want electricity conducted in places we don't want it, right? These traces are, fractions of a millimeter wide, and a little piece of salt crystal will conduct electricity where it doesn't need to go. But the people who do this for a living figure out a way to build all this stuff so that you can test it that way, or so that you can deploy it in those environments, I should say. All right, thermals. How do we get the heat out? If you want to do this for a living, and I do not, you actually have to learn some math. The good news is that I don't, and you probably don't either, so we're not actually going to learn the math. What we are going to try to remember is that some of these things become nonlinear. And when it's not linear, the stuff that is not terribly obvious as to why it's hard becomes a little clearer as to why it's hard. But almost anytime you look at something and say, why is it built the way it's built? It's usually because we got up to where the curve started to bend and then said, nope, that's too expensive. We're not going to go any further. All right. What are the key characteristics of air as it relates to how we use it to cool things? Somebody go. Anybody? Sorry? Yep. 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 So basically the properties of air are how much heat can it conduct, which is basically a function of, it's like a physical constant. It has some unit that my wife, who has a PhD in chemical engineering, could probably explain to me. The inlet temperature, the air flow rate, the surface area, which is basically how many molecules of air, because if you, I promise I won't do a lot of the physics. If you drill all the way down to it, heat transfer is basically a molecule of something bumps into a molecule of something else, and energy moves from one side to the other. Like, that's basically what heat transfer is. Sorry, Michelle, I know that's not totally true, but that's the way I think about it. And so in order to make this more efficient, I can either bounce more molecules, I can increase the difference in temperature between the two of them, right? Because like cold air moves heat better because the heat transfer function has the delta of the temperature in it, right? So if two things are the same temperature, they don't transfer heat. If two things are in wildly different temperatures, they do transfer heat. That's thermal conductivity. One of the intriguing things about air is that it is absolutely the worst possible medium for transferring heat that we can come up with the possible exception of a vacuum, right? I think you call them Eskies down here. What is an Esky lined with? Styrofoam. What is styrofoam? Air. It's an insulator. It's not a conductor. It's a terrible conductor of heat. It's an awful conductor of heat. Why on earth do we use this thing that is unbelievably awful at conducting? Oh, because it's free. That's it. It's because it's free. That's the only reason we use it, is because it's free. So we take this thing that we have lots and lots and lots of that's basically free, and we pump it around, and then we try to move the heat that way. So who can tell me what are the key inputs for how we cool things with liquid? Yeah, it's exactly what it is. They're the same. But all of the exchange rates are really different, right? the thermal conductivity constant of water and most of these engineered fluids, because we don't actually use water for most of the stuff. We use slightly modified water or some really, really, really fancy engineered fluids. But it's basically the same set of equations, right? It's the fluid flow rate. How different are the temperatures? How much surface area do I need? And what's the conductivity of it? So we've basically taken all the same equations. Like if you sit down and pretend to know the math, but if you sit down and pretend to know the math, all you've changed is the coefficients, right? It's all the same. Like the math is all the same. It's just now the, watts per meter square per second, that might actually be right, that I can transfer with this, super fancy Castrol or 3M engineered fluid. That number is just way, way, way higher than air. And so now I have to figure out how do I move all this stuff around in a system and not break all of the other things, right? So the inlet temperature matters a lot. Generally speaking, because the thermal conductivity is so much higher for these fluids, that's really the thing. That's really the magic, right? The number that really, really, really changes here is the conductivity, the ability to absorb heat for all of these fluids might actually be orders of magnitude higher than air. And so when that number changes, like once you jump off the cliff of all the mechanical engineering to get this liquid to either the device you're trying to cool or to the cold plate that's attached to the device you're trying to cool, all of the other things become way, way, way easier, right? You don't have to move nearly as much of it because the conductivity is so much better. So again, it's all basically the same equations, they just have very, very different coefficients. So a little bit of the liquid cooling word cloud here. CDU is coolant distribution unit. That's a catch-all term for any number of things where you literally distribute the coolant. You can have sidecar cooling, which is basically you have a heat exchanger on the side of the rack. You can have end-of-row setups, which is exactly what it sounds like. You have this big heat exchanger at the end of the row. There are lots and lots and lots of different places that you can put the equipment that does this. And that comes down to, how tightly integrated is it to the facility, right? If it's a brand new custom-built data center and you know exactly how much power every row and every rack is going to consume, you can engineer the building, which is what people are doing for these new builds. You're engineering the building around the mechanical and power envelope of what goes in it. If you are calling up some random colo and saying, hey, I would like to put some gear in your building, they're going to say something like, okay, I charge you this much per rack and it can't have more than Y number of watts because that's how much aircon I've got. So you end up with lots of distinction in the way that those buildings are built and integrated. You can do things in the rack where you literally put a heat exchanger either in the front or the back of the rack and you blow the air over that heat exchanger, which makes it colder before it gets to the gear, or it cools it after it comes out of the gear. The terminology that you'll hear sometime is these efficiency metrics, WUE, PUE, CUE. Anything that can get measured can get managed, right? Some famous business writer said that one time. Take any number you see here with a substantial grain of salt, right? Because it's probably come from somebody trying to sell you something, including me. But these are the metrics, right? At some point, what you want to do is more efficiently, generally what you really want to do is more efficiently use the power, because that is more often than not the actual scarce resource. And then if you'd like to do the mechanical engineering stuff, there's a whole universe ecosystem of companies that build all of these fittings and couplers and manifolds and water feeds and water returns. And it's like this never-ending black hole of interesting mechanical stuff. And if you go to some place like OCP or some of those conferences, like they have entire conferences for people who like literally just build couplers. It's wild. For the most part, this is where we are today. There were lots of stuff. It's super cool to put stuff in gooky-looking thick water and watch it boil. And the physics are really, really, really on your side here, because phase change heat transfer, like if I boil water, it takes orders of magnitude more energy to boil water than it does to raise liquid water 1 degree. Right? I don't remember the numbers, but it is astronomical. Like to boil a gram of water from 100 to 101 is astronomically more energy than to move it from 99 to 100. The problem is that it's messy and it's really hard to work with. In some cases, you end up with problems like where the fluid gets between the optic and, again, that little teeny tiny but not zero gap between the end of the fiber and the thing that it mates to. Well, those things are all engineered for it to be air, right? There are optical properties of air and there are optical properties of whatever this magic unobtainium fluid is, and they're not the same. And because they're not the same, these optics may not work the way you expect them to. So where OCP, which is, I guess, the closest thing we have to a set of standards here, almost everything you're going to see in the near future looks kind of like this, right? These are, somewhere in here, these are giant cold plates that sit on top of the components, and you pump fluid through this. It's almost always copper, because copper doesn't corrode that badly and is very, very, very good at transferring heat. And so you're going to see more direct cooling, at least in the short term, than you are immersion. Although we'll see where that goes. The key bits of the system here, the TCS, technical cooling system, basically these are just heat exchangers. Right, now if anybody got a mechanical engineering degree, A, please leave because you now know that I'm full of it. And B, a heat exchanger literally does that, right? It takes heat from one side of the system and moves it to the other. There's a whole universe of ways you can do this, but it basically comes down to how do you manage it, right? You have to make sure that the thing isn't leaking, and you're probably not willing to pay somebody to walk around the building and look for leaks. So what that really means is you need an entire system that can figure out things like, did the pressure change in that pipe? And if the pressure changed in that pipe, did it change where and by the amount that I expected it to? Because if those numbers aren't right, then I might have a lot of water on the floor. And as much as these things don't like having fluids, a lot of these systems don't like having fluids. They really don't like having them in the places they're not supposed to be. So you've got all these, you've got all these couplers down here. Like, again, there's a whole universe of how these things are built. It's super fascinating. This is a manifold heat exchanger. This is called a contraflow heat exchanger, which basically means that the hot comes in one side, the cold comes in the other, and they flow opposite each other through the entire loop. And the reason you do it that way is because at the opposite end, whatever the temperature at the input was, it basically flips. Whereas, like, if you pour hot water and cold water into a sink and mix it, you get a lot of water at the average temperature. But if you do a counterflow heat exchanger, you actually get all of the heat out at the other end. I had no idea how that worked until a friend of mine who brews beer said, no, it works like this. I was like, oh, that's cool. So anyway, not a brewing conversation. Real quick show and tell. These are the demos that we've done within the last 6 to 12 months. Again, the schematic here, the red pipes are the hot water, the blue pipes are the cold water. This is the cold plate. Generally speaking, you've got if you're doing servers, it's usually the GPUs and to a lesser extent the NICs. If you're in a networking piece of gear, it's usually the big NPU that sits in the middle and the optics. And these are the things that are the most thermally sensitive. To some degree, everything is thermally sensitive to some degree. But these are the kind of things that we show and tell for demos. All right. Board design. Not this. Also, not this. But this is a little closer to what we do, right? Somebody says, I want to build a 28.8 terabit line card that moves lots and lots and lots of packets per second, because if I do that, I'll get rich and famous and the world will be great. The problem is that, so this is just the fabric card for one of our really, really big systems. And this is like the first step down the rabbit hole. So like you literally go into our document management system and I find something like fabric card, 18 slot, hardware design spec. I'm going to pretend to be a real engineer, go. And it gives me this several hundred page document. And one of the things in the several hundred page document is a block diagram that looks like this. Like, ignore what all this stuff is, but each one of these little guys here is a discrete signal. That is at least a pair of traces somewhere that I have to wire from one of these components, whatever the heck this is, out to some kind of either circuit board trace or a connector. and then it comes back in some other place. This is one of the control FPGAs for the board. So like it would be, I don't know, something like that chip right there. Not one of the big ones, one of the little ones. There are hundreds of signals just on that little chip. There are dozens of those chips, and never mind that once you get to these really big ones, like these things have like 5,000 pins. So I've probably got something like 30,000 signal pairs that I've got to route on all this stuff. I've got the really big stuff that we think about, right? The network processing units, the retimers. Like these are the things that run really, really high-speed signals. They use a lot of power. They're really sensitive to the quality of the circuit board, and you have to like really, really, really carefully engineer this stuff. The optics are the same way. They're very sensitive to temperature. The high-speed optics, not surprisingly, run really, really high-speed signals. So I can't just arbitrarily drag, like if I want to run a signal from the chip to an optic module, like this is a bad choice, right? Because A, it's really far and the distance hurts, and every time it bends, that also hurts. Because the signals want to go across really short, really straight runs. And anytime it's not short and it's not straight, that hurts the signal integrity. So then you've got, power rails. I've got to get power to all this stuff. So like you look at the board design, and if you turn the board flat and look at it sideways, there are basically layers through the board that exist basically just to carry power to all of these components. And those obviously have to be engineered really carefully because you don't want to use too much board, you don't want to over-engineer the thing because it's expensive. And then you're using space that other things can't use. And if you under-engineer the board and you can't get the power to the chips, then it turns out they don't work. So we don't like to do that either. Why is this hard? Like, why do board designers who do this get paid a lot of money, and why are there very, very few of them? The metaphor I've come to is it's much more art than it is science. And a lot of it just comes down to this is not a computable problem, right? If you think about the board design problem, it's basically a traveling salesperson problem with thousands and thousands and thousands of possible stops. Like, at least not yet, and maybe the AI overlords who are coming will also solve this problem, but you cannot currently give a computer program and say, I want these 4 chips to be laid out to optimize the signal integrity and the power usage problem. I'm going to go have coffee. I'll come back in a day. You will have done all the math. It doesn't work that way because it's basically a factorial complexity problem. Because if I move any one of these components even a millimeter, everything that it touches has to also adapt, right? And if the tolerances are super, super, super wide, right? Like if everybody's got lots and lots of margin, then yeah, I can move this thing around and everything will still work. But we don't build at the high end, certainly, and pretty much everywhere else. Like we can't build stuff that has lots and lots of margin because there just isn't any margin left. When I talked about the exchange rates changing over time, one of the things that has become really, really difficult is these super, super, super high-speed signals need to be really, really short. And I can put a retimer in there, which is literally a microchip that says, all these signals that came in, I'm going to listen to them, clean them back up, regenerate them, and send them, it's an optical regen, it's the same thing, and send them back out the other side. The problem is that those things take space, and they take power, and they cost money. And it turns out you guys don't like giving us any more money than you absolutely have to. So there's all of these kind of competing intention parameters that I'm trying to optimize for, but I can't do it all at the same time. So it really does end up being much more of an art thing where, you'll say to somebody, and the people who do this for a living, you can say, oh, I'd like to build a board that works like this. And they can immediately say, that won't work. I can't do more than 3 of these because, and at some point you just have to sort of take their word for it because they've done it for 30 years. All right. We spend a tremendous amount of time figuring out how to get zeros and ones from the left side of something to the right side of something else. Again, not a double E. Took 1 circuits course in college, didn't really enjoy it because it turns out there were like integrals and derivatives, and I'd had just about enough of that. was like, I want to work with zeros and ones. What is signal integrity? Well, I Googled it, and I got something like this, and I immediately panicked and said, I don't want any part of that. It's this. We spend, like I have an entire team of geniuses who get paid a lot of money and spend their life basically trying to figure out whether the thing coming down the wire is a 0 or a 1. Right? It is literally, telephone string and somebody screaming 0 or 1, what am I doing? These are all the terms, right? If you'll let me abuse the metaphor a little more, right? The channel is the thing that carries the signal from the sender to the receiver, and we try to fight the noise problem, right? This is, like, I feel like I could give a relatively bright 10-year-old this metaphor, and they'd run off and want to get a double E degree, and then they also figure out that there's really hard math, and at that point, it's not nearly as much fun. Or maybe it is. So the way we measure signal integrity, or at least the way we visualize it, I guess, is with this thing called an eye diagram. What this basically comes down to is every so often, we have to look at the value of something. It's usually the difference in voltage across two wires. That's usually the thing that we're actually measuring. In the optical domain, it can literally be, is the light on? Or it can be, what color is the light? Or it can be, whatever the parameters are. One of the things that one of my hardware engineering friends said to me once that was so obvious when he said it and had not been until then was, in a small enough time scale, everything is analog. And I was like, oh, that's super useful, right? We think of things as zeros and ones. There is no such thing as a 0 or a 1, right? If you go and look at a square wave, and sorry, again, math, but just a tiny bit. If you go and look at a square wave and then you think maybe you took that course in college, how do you make a square wave? You take a bunch of fancy sine waves and add them together, right? I had to go Google Fourier transform or Fourier series or whatever the heck it was. And I was like, oh, right, it's not a square wave. It's actually a continuous function that if you zoom out enough, it looks like a square wave. It looks square, but it's not, right? In the real world, in the analog world, there are no corners and there are no gaps, right? Everything is some continuous value, right? It takes non-zero time to change voltage. It can be so fast that if you zoom out, it looks instant, right? You hit the light switch, the light comes on. Like, if you zoom in long enough, the voltage changed, the temperature of the filament changed, because we're going to talk about incandescent light bulbs here in a minute. And that all takes some finite measurable amount of time. What we're basically doing with all of these signal integrity problems is, every so often, on some determined clock frequency, I measure something, right? And I measure voltage, and I get some number. And then I figure out the number of volts or differences in volts or whatever that I just measured. I need to map that to some other value. And sometimes I can literally say, if it's high, I'm going to call it a 1, and if it's low, I'm going to call it a 0. And then between now and the next clock tick, I might stay at the same voltage, in which case it's still a 0, or I might transition up to another one, now it's a 1, right? But this is all analog, right? At some point, this is all continuous. And this is how we used to do things for trillions and trillions of years. In order to go faster, what we can't do, sorry, not fair. It has become very, very, very difficult in a nonlinear way to make this stuff go twice as fast, right? Doubling the underlying sample frequency from where I am is extraordinarily hard for reasons, physics, I don't know, but it's hard. So one of the many things we've done is we've basically now said, instead of only deciding whether the thing is high or low and turning that into a 0 or 1, I'm going to say, what is the level, right? Now it's going to be 0, 1, 2, right? Instead of measuring 2 possible levels, I'm measuring 3 possible levels. So you can theoretically do as many of these as you want. Right, like PAM4, pulse amplitude modulation 4, is basically now I have up to 4 numbers that can come out of there. And it's not high or low, it's 0, 1, 2, or 3. Well, if I get 4 possible levels, that's 2 bits, right? So what I've basically done is, in one time slice, instead of encoding a single bit, I've encoded 2 bits. Who here ever used a dial-up modem? Yeah, Like that's all a modem was. Like the squeak, squawk, squawk, squawk stuff. Like the SerDes on our boards do exactly that. They literally come up and they try to connect to each other and they train and they talk back and forth figuring out how fast can you talk? Well, I can talk this fast. Can you talk a little faster? Well, I can, but I might have to use a little more power. And they do that whole auto negotiation thing. And it is literally exactly the same process that US Robotics and 3Com and Hayes were doing in the late 80s and early 90s, going squeak, squawk, squawk. Whereas back then it was 24 kilobits a second, and now it's 224 gigabits a second. But it's all the same concepts. And basically what you get is, when you look at this on a scope, if the power degrades over time, it takes the eye diagram and it does this, right? It just squishes it vertically. And at some point, the reason they call it an eye diagram is if this eye here or here closes, I can't tell what the number was, right? If this thing, see how it gets all fuzzy here? If this fuzziness touches this fuzziness, I can no longer know, is this actually the thing at the top or is it the thing in the middle? And so all of signal integrity is basically, as the power goes over time, right? You drop the signal drops, it gets squished this way. When you have two traces on the board that are not exactly the same length, the signals don't arrive at exactly the same time. So one of these waves shifts. The time domain here is horizontal. The time, it shifts this way, right? So now all of this stuff starts to shift to the left or starts to shift to the right. And as you get noisy, the whole thing, and eventually if you get to the point where this is no longer visible, you're done, right? You now have to fix something. So how do we fix it? Well, you can shout louder. Easy, right? Only problem with that is sometimes you actually can't shout any louder. I don't usually have that problem. But it takes more power. And we don't like power because power's heat. You can talk slower, which I also don't often do, because that basically takes the whole thing and stretches it this way, right? If you reduce the frequency, you now have a longer period of time between when you measure the value and you measure the next one, so it's more tolerant of all the other stuff. You can get closer because basically everything we use has some amount of noise and loss that gets introduced by distance. Anybody who's done optical planning understands this, right? The fiber itself has some number of decibels per kilometer, and you do the math and it says there's this much loss that's happened in the system. You can get better string, right? We spend a lot of time working with the vendors who build the actual boards in like the materials that those boards are built out of. It's not just, they don't just throw that stuff together, right? It's really, really, really pure copper, mostly copper for the traces. And then all of the insulating materials that go around those copper traces, like we have to be really, really specific as to, you know, the term is dielectric coefficient, maybe, I think. It's basically how good an insulator is it, right? Because you want that signal isolated to the trace, and you don't want it bouncing off against the walls. There's entire PhDs can easily be done in how this stuff is designed. And then the other way to do it is just remove the background noise, right? And that comes down to things like if I want to run two traces next to each other through some part of the board, there's going to be crosstalk across those two. This is the stuff where, you know, I talked about how you can't compute this stuff. Like you can't ask a giant software package to do the board design for you, but you can, and we do, ask a giant software package to validate and confirm whatever our design is, right? Because I can say, I think the board's gonna look like this. Here are two traces. They're X number of micrometers wide. They're this thick. They carry this many volts at this many amps at this frequency, blah, blah, blah. And then you can sell the machine, go run the math and tell me what do you think is going to be the answer at the other end. Right? And generally speaking, you can model this stuff pretty well. And at the other end, it will say, I don't think you're going to be able to figure out whether that's a 0 or a 1. And if that becomes the answer, then you kind of go back and say, I got to change something, and you try again. Right? And so doing board design is really this like iterative process of how you work through that. All the different, I'm going to walk through some different-ish ways that we build this stuff. This is sort of like the generic version of almost everything. You can swap in a couple of terms and it looks kind of like this, right? If I've got a line card or a switch, it's got a chip in the middle, sometimes more than one. These little yellow lines are the traces that run through the PCB. A lot of times I'll have a connector onto a backplane or another line card or some other piece of equipment there. Traces up here, whether these are electrical optics, I use that term very, very loosely, right? Sometimes these are like direct attached cables or active electrical cables. Sometimes they're optics. But the whole point here is that I've got some amount of signal that either originates over here or I want to send over here, and I've got to get it through this whole thing. This is basically your loss domain, right? At some point, a 1, or whatever the hell this thinks is a 1, comes in over here, and I want a 1 to go out on that wire. And figuring out how do I do that, and in the old days, it basically just looked like this, right? Because the limiting factor wasn't usually the PCB. It was, and I mean, it's always a limit, right? I can't make these wires arbitrarily thin. I can't make them arbitrarily thick. But in fairness to the people who do that design, this part was easier. This part is no longer easier. This part is now very, very hard. Because as you increase the signaling rates, and so in the stuff that we're using now as we go to 200 gig analog, the underlying signal rate is 62 gigahertz. So that means that every 16 picoseconds, I think I have that right? Yeah, every 16 picoseconds, I have to look at something and not just figure out if it's a 0 or 1. I got to figure out which of 4 or maybe 6 or maybe 8 different levels is it, and then I have to turn some series of those numbers back into zeros and ones. And so if you walk around and look at how these systems are being built, this is kind of if I look, this is kind of from the top down, if you will. Like this is how it used to be, right? This version basically corresponds to the trace above. Who's got the little two-handed? Oh, that one. Yep. So that guy is basically a flyover cable mated to a connector in the back. And if you remember that cable, each of those, instead of being like a single PCB trace, which are fractions of a millimeter, each of those is a shielded cable, right? That's basically the same physics as cable TV, right? That's just really, really, really small coax. And because it's coaxial, it's way more tolerant of signal integrity math. Please don't ask how, I just believe it to be true. Again, there's a reason that cable TV has been around forever, and you can send a lot of data down a coax, and we've been doing it for 50 years. So what we've basically done is replaced some of these PCB traces with these flyover cables, right? This is just a whole bunch of little tiny twin-ax cables, and each one of those pairs of cables, I can measure the voltage difference across the two of them, just like I would across traces on the PCB, right? That is just way more expensive, a lot heavier, but it's way, way, way better for signal integrity. Right? That's the trade-off I'm basically making. And so you can essentially replace that whole schematic is basically data coming in, data going out. How many different steps are there? And what are the trade-offs at each of the steps? And so you can do that. You can take this little E. This is a electrical to electrical conversion. It's basically that little pressure mate connector. And so I can take the chip and I can drag the signals that far, right? And it's way easier to drag high-speed signals this far than it is to drag them this far, like way easier. And so instead of trying to send a really high-speed signal across this much circuit board to the optic, I send it this far to one of those connectors where it jumps onto that flyover cable, goes over to the mirror version of that little electrical to electrical connector, and then drops it into the optic. So what I've basically traded is a lot of like mechanical complexity and a lot of wiring and a lot of potential reliability as I have to solder all these things onto the board or compression fit all these things onto the board. And what I've gotten is something that's way more tolerant from a signal integrity standpoint. All right, that's basically just another optimization exercise. And somebody sits down and says, usually what it comes down to is somebody says, we simply cannot go faster doing it the old way, right? There's always somebody that's trying to figure out like what's the new thing and people doing research, and that's really cool. Where the rubber meets the road and people want to buy and sell stuff to run their lives, it usually comes down to the way we used to do it just ain't gonna work anymore. And so now we have to figure out a new way. And so one of the new ways is that. And then by extension, you can do a lot of the same things, right? You can take these and you can do circuit board traces, you can do flyover cables, you can drag those to, instead of having a backplane with a bunch of fabric cards and a lot of logic back there, like you'll see some of these really, really big integrated systems where in the back, they just have this gigantic fiber shuffle or cable shuffle, which is nothing other than this, it's basically a giant optical cross-connect board, but it's pre-wired so that when it gets to the back, you've basically built your mesh interconnect in the back out of all these fibers or cables. And you can do exactly the same thing with optics. But what you really end up doing, right, the whole thing is I'm trying to replace this high loss, not terribly tolerant of super fast signals with something that is more efficient at getting the signal from the left side to the right side. And that can be a copper twin-ax cable. It can just as easily be an optical module, right? Because one of the other things that you're seeing, we're going to talk about here in just a second, is what they call co-packaged optics or near-package optics. That is basically nothing other than instead of dragging the electrical signal this far to the optics that plug into the front of the switch, I'm taking the laser and moving it a lot closer so that I don't have to drag that signal very far. And then because once I get it onto optical fiber, the loss rates for optical fiber are orders of magnitude better than they are for anything electrical. Now they're more expensive, but like we've known this forever, right? The reason that the modern internet is built out of optical fiber instead of copper cables is because you can drive a lot more data a lot further across glass than you can across copper. All right, so optics. Quick history lesson. Once you got to about a gigabit, the way we start making this stuff go faster is some combination of higher signaling speeds and more parallelism. And so what you almost invariably see is, the very, very, very first 10 gig E optics were, 4 by 2.5, right? They weren't actually 10 gig. They were 4 by 2.5, and we just multiplexed it inside the module, and at the other end, we unmultiplexed it, and it just looked like a 10. And so the very, very, very first 100 gig module that I can remember seeing on the ASR 9K was about the size of my hand. It probably weighed, I don't know, 300 or 400 grams, something like that. And it was like $150,000. And I remember one of the engineers handed it to me and he said, "Do not drop this." Said, A, we can't get another one, and B, this is worth 10 times what your car is. I was like, okay. And so what you end up doing is as the SerDes speeds, as the analog speeds get faster, it kind of unlocks these higher speed interfaces, and then you have to figure out how many of them in parallel do I want to build, right? And so the leading edge thing, and you can take this whole time series and basically over time just shift it this way, right? And so over time you just get more parallelism and higher underlying rates. This is the part that makes the signal integrity part really, really hard, right? Having 16 parallel interfaces is really just a space problem, right? If I can drive 2.5 gigs this far, I can drive 2.5 more gigs right next to it. But if it becomes 5, I can't go that far. And if it becomes 200, I definitely can't drive it that far. So what we end up with is, we end up with some combination of more complex encoding, right? This is, IMDD is intensity modulation, it's direct detect, right? You are basically directly reading the value of the light and turning that into a number. When that is no longer sufficient, you do what we call coherent, which basically says I am taking some combination of the frequency, the amplitude, and the phase, and I'm measuring multiple dimensions of the light, and I'm turning that into multiple levels of signal that I can then turn into bits. And so the more complex the modulation is, the higher the bandwidth, but it also costs something, right? It costs silicon, it costs money, it costs watts, it costs complexity, all that sort of stuff. So one of the ways that you attempt to mitigate that is with all these different error correction magics. And so that is basically you send more bits than you actually need so that at the other end, when some of them have been flipped or can't be read, you can recreate them. And there are PhDs full of mathematics on the 7 million different algorithms that there are. There's really only about a half dozen that anybody actually uses. But it's super, super interesting stuff. Again, that costs something, right? I have to have logic to do all the math. And that logic costs money, and that logic uses power, and that logic takes up space that I could use for other things. So the optimization exercise is how far do I want to drag this signal before I can't figure out whether it was a 0 or 1 anymore. So what you kind of see is this, again, as the distance increases, the crossover for where it sort of makes sense to do one versus the other adapts over time, right? So the coherent stuff is going to keep getting shorter and shorter because the data rates are getting higher and higher. I don't think, I stole this slide from Mark Noel, I don't think he's here this year. But if you're interested in this sort of stuff, come find me and I can get you name and links because his Cisco Live presentations on all this optical stuff are super, super good. And he does way, way, way better justice than I ever could. From a kind of mechanical engineering standpoint, like why we really care about this is all basically doing the same thing. But what you find is over time, you just integrate more and more stuff, right? So MCM, this is multi-chip module. Each one of these is basically just a smaller version where more and more of the components are integrated into a single circuit board, right? There's in a 800 gig or 1.6T optic module now that runs at 25 watts or something like that. Like there's a 3 nanometer DSP that is every bit as complex as the world's most complex supercomputer from 10 years ago, right? Like all of this kind of silicon magic integration, one of the places you really, really see it is in how you can make these optics super, super, super small. And so what you end up with is, and there's lots of acronyms and lots of time over here, but each of these things, as it gets smaller from a mechanical engineering standpoint, that's great, right? The optics get smaller, I can cram more stuff into a switch that's only this big. I've got an NPU that can do 100 terabits now, so I got to get all those bits onto optics to get them off the chassis. But I've also got to keep all this stuff cool. And optics really, like silicon chips don't like being hot. They can't run at more than about 100 degrees centigrade. Optics really don't like being hot. They can only run about 70. And not only do they not like being hot, but they also don't like being cold. And so in the optical universe, as we get to, that's what happens when you steal a slide from somebody. As you get to co-packaged optics or switches that kind of where you put the optic modules on or right next to the NPU, one of the problems you have to solve is I have to get the lasers, and it used to just be, well, it can't be more than 70. No problem. I'll put a big heat sink on them, I'll blow the fan, maybe I do liquid, whatever, no problem. Now it's, not only can they not be more than 70, but they also can't be less than 65. And so I have to take these optical modules and I have to get them warm enough to run, but then I have to very, very, very carefully manage the way that they're cooled so that I don't take away too much heat, because the way this was explained to me, and again, I don't totally understand it, is the frequency of the light from these generators varies with the temperature of the module. And so if it shifts too much, all of a sudden the thing that you're using to carry your zeros and ones is now carrying a 0.49 instead of 0.51, and when you round that, you get the wrong number. So what you're sort of seeing in the optical domain is there's the retimer. This is a digital signal processor, which basically just takes this presumably really noisy signal that comes in from the chip, and we turn that back into zeros and ones before we hand that to the optical engine to spit those things back on the fiber. And so you're basically just moving how much of that you want to do, and what it creates is trade-offs on the silicon side, right? This is kind of what we do today. You have this channel, right? This is a normal SerDes that goes from the chip to the optical module, and there will be a spec on the module that says, I can listen at negative 35 decibels, whatever, some number, right? And so the chip and the channel, the board designer basically has to say that at this point right here, I have to get some quality of signal, and the other guy says you'll be able to understand it. Great. If you can make the SerDes and the analog better on one side, then you might not have to do as much math in the module. Right? This is the optimization exercise. And so here you can say, so this is called a transmit retimed optic. What this basically says is the signal is good enough in this direction that I don't have to do the retimer. Right? This is a bunch of math. This is a bunch of transistors. This is a bunch of watts. This is a bunch of money. This is a bunch of stuff that I don't want to spend if I don't have to. And so in a perfect world, I wouldn't have to do any of this math, but it basically comes down to an optimization exercise of if I can make this side good enough that this thing can figure out whether it's a 0 or 1, then all of that extra silicon goes away. And if I can throw that silicon away, the module uses less power, and the thing that is really, really thermally sensitive and really expensive is now easier to build. Right? So the exchange rate here becomes, the question becomes, is it easier, more efficient, smarter, whatever metric you want to use, to do it over there, or do I want to do it here? And like most of these questions, there is no absolute answer, right? You can solve these things in different ways. But that's what we do there. This is just kind of a reference sheet for the different physical form factors for optics, which I won't go into. Where I started this entire presentation when I was like, what's something really cool that I wanted to think about? How hot is too hot, right? These things, they're really sensitive to temperature, and most of this stuff, if you get them warmer than X, they let the magic smoke out, and then they don't work anymore. So I started thinking about like these really, 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 high-power chips that we work on. The filament in an incandescent bulb is about, who remembers an incandescent bulb, right? If I come back here in 20 years, people aren't going to know what I'm talking about. I'm going to find a new metaphor. The filament itself in an incandescent bulb is about 2,500 degrees centigrade. The glass around an incandescent bulb is about 250 degrees centigrade. Don't touch it. The modern NPU, the junction temperature is about 100 degrees centigrade. If it gets hotter than that, it doesn't work anymore. The optics tolerate somewhere in the mid-70s, and you can touch something for, I think it's 1 second if it's 55 degrees centigrade, and whoever makes these rules says that's not going to burn you. So, which is hotter? The heat coming off of one of these 100-ish terabit NPUs, or the heat coming off a 120-ish watt incandescent light bulb? Like, I thought about that question and went, I have no idea what the answer is. I know I'm not touching a 100-watt incandescent light bulb. I was going to bring a 100-watt incandescent light bulb for show and tell, but I couldn't find one. Right? Like think about how hot that thing gets, and think about how close you're willing to get your finger to it. It turns out that these chips are like an order of magnitude hotter than a 100-watt incandescent light bulb. I had to cheat and put the math up here because I knew I'd never remember it. So a 100-watt light bulb is about 8 kilowatts per square meter. Now granted, the square meter would be a giant light bulb, but like a normal fist-size light bulb is, I don't know, 4 centimeters or 5 centimeters in diameter or something like that. It's like 8 kilowatts per square meter. One of the chips we build is 500 kilowatts a square meter. The thing is, go downstairs to World Solutions and look at it. It's like that big square, and it's north of 1,000 watts. Actually, sorry, the package is that big. The chip is actually more like that. It's like 2 or 3 centimeters square, and it's 1,000 watts power coming off that thing. So the heat sinks that you have to engineer have to be real. This is why we have to start cooling things with liquid, right? Because at some point, even these super advanced heat sink designs where we've got like this one is basically a vapor chamber. So you'd put fluid in here, and you have this It's not extruded. It's like puffy copper. And the reason it's there is to dramatically increase the surface area, right? So that as the fluid comes into this called a vapor chamber, heat pipe vapor chamber, as the fluid comes in, it's got all this surface area, and you want it to flash into a gas, which absorbs all of this heat, and then it basically naturally convects through the system. The other thing is, we've got all these basically machined channels in all these heat sinks. This is 100 micrometers. So like the amount of surface area that you go in and generate here is way, way higher than the way you do it there. So all that sort of stuff, and even inside these cold plates, when we first started doing liquid, you could basically say, I'm going to do liquid cooling. It's so conductive. It's great. It can suck so much heat out of these cold plates that I don't have to really pay that much attention to what the heat sink itself is made out of. It's just a thin-ish slab of copper. Well, at some point we go, oh, nope. Now we're talking about 3,000 watt GPU complexes. And in order to get that much heat, now I not only have to have the liquid cooling thing, but now I also have to have these, super highly engineered heat sinks. I have 2 copies of these slides in here. Sweet. All right, last topic. For chips, from the mechanical engineering, this is the part I really like. There's this new thing in silicon design that's generically called advanced packaging, which is not this. It is basically, instead of having one chip on one package on one circuit board, which is the way that things basically worked forever and ever, right? You had, you go back to building your computers, right? You had a motherboard, and then you had the CPU, and the CPU sat in a socket. Done. Take that metaphor and just add multiple layers, right? You will hear people talk about 2.5D packaging and 3D packaging and HBM memory and all this fancy stuff. All you're really doing is taking another layer of abstraction that sits between the underlying circuit board. And so now you might have the circuit board, and inside, like if you go downstairs, one of the chips we have down there, actually that's the next slide, this guy. So this is one of the chips we built downstairs. So it's a little hard to see in the picture, but the main die is this inside square here. These 2 guys are memories. And then 1, 2, 3, 4, we call them chiplets. So this thing is actually 7 individual semiconductor dies that are assembled onto this other piece of silicon. It's just a big microchip. Like the substrate that we put this on is exactly the same manufacturing process as the leading edge silicon thing from like 10 years ago. And so you take a bunch of really, really modern chips, put them on a less modern chip that functions as a circuit board, and then you put that inside the big rectangular mechanical package so you can get all the pins out to the bottom, and then you put that on the circuit board. And kind of the next extension to that is you're going to take that and you can kind of stack these things arbitrarily high. At some point you get into real world limits. But all of this stuff, like there are about 70 different voltage and temperature sensors on this thing. And so I have to keep track of how hot is it, not just how hot is it, but where in the heat is it. Or sorry, where on the chip is it, right? We've got designs, silicon designs now, where I would be able to put the memory this close to itself, right? I could say, I'm going to do 10,000 rows of memory in a millimeter. And I can physically manufacture that, but I can't cool it. Because I now have so many transistors in such a small amount of area that even on the chip, I can't get that much heat away from that small an area, right? Because now you're talking about that heat flux that was, it was 500 kilowatts a square meter. If you look at the hottest spot on the chip, it's probably 20 to 50 times that. And then if I concentrate that even more, it's going to be another double or triple that. And so at some point, I've started to build the silicon in a way that I can actually cool it, given whatever the technology is that I have available. All right, that's pretty much it. Hardware's hard. Takes a long time to change things. and everything's a trade-off. Who's got questions?